Next session on mathematics for quantum computing. Your valuable cooperation and feedback are greatly appreciated as they contribute to the continuous improvement of our upcoming sessions. MyQuantumTechnology is your partner in quantum computing journey, providing innovative quantum computing training and solutions. MyQT is a repository of world-class knowledge and wisdom contributed by the best minds in the field of quantum computing. MyQT operates across the globe through its vast network of affiliates and partner organizations. MyQT provides a wide range of offerings, including training, certificate courses, research opportunities, and consulting services. I welcome Deepa ma'am to introduce the speaker to you.
Thank you. Okay, now it's time. Thanks, Christy, and it's time to welcome our speaker, Subodh. Welcome to the section. Currently working as a software developer, Subodh spends his time solving system architecture and implementation-based challenges. With a combined background in AI and quantum, the major research domain he explored was quantum machine learning. His research has taken him to quantum cryptography, core quantum computing, and machine learning as well. And now here I mentioned some of his hobbies. That is, he's fond of reading books, playing chess, and cooking. Currently, working as Associate Solution Leader, Brainy Enterprises Hyderabad, he has published a title. That means he has published a article, that is Quantum Search for Lightweight Block Suffers, GIFT, Skinny. And he is also interested in problem solving, quantum computing, AI, and engineering. Now it's time for Subodh's study section, and I again hand out over to Christy. Please continue, Christy.
So now we are all waiting for your talk, sir. So welcome, Subodh sir, for your talk.
Yeah, thank you, Christy. Thank you, Deepa. I'll just share my screen. Excited. I hope I live up to the things. Okay, hello everyone. I'm Subodh. I'm currently an associate solution leader at Brain Enterprises. My work is mostly in NLP, machine learning, and software development, and I work on the architecture side of things. How I came across quantum computing was in my master's research. So 1 year of my complete research spent on developing quantum machine learning algorithms, and from there only myself and Karthik Ganesh made. So today we'll do an overview over the mathematics that will require for quantum computer, and just a very 10,000 feet, as KG says, 10,000 feet above view of it. KG will take it forward from there, but I'll give you a brief introduction or a brief environment of how the quantum computing framework works. Okay, you can ask me any questions in between. I don't have a problem with that, but we'll keep it to the end if possible. So mathematics for quantum computing. So the agenda will go through the introduction of quantum computing. Let me just put on the laser pointer. So that we'll go to the introduction of quantum computing. We'll look at the quantum states. We'll look at what a block sphere is. We'll see what the quantum states and the properties are, and the three most important things I can say: superposition, entanglement, and measurement of quantum states. We'll also look at some part of linear algebra that is required for quantum mechanics, and I'll give you some introduction about quantum algorithms, and we'll look at the future of quantum computing. So how I got interested in quantum computing was because of this experiment by Google, the quantum supremacy experiment, which basically states that a quantum computer can perform a task which a normal supercomputer, even not a normal computer, a supercomputer will take a lot of time to perform. So it states that quantum supremacy refers to the milestones of the quantum computing where a quantum computer can perform a specific computational task that is demonstrably beyond the capabilities of classical computers or even supercomputers for that matters. So it signifies the point at which a quantum computer can solve a problem or execute an algorithm in a significantly faster or more efficient manner than any known classical computing technology. So what Google did was they used their 53 qubit quantum computer. I will tell you what a qubit is going forward, but they used their 53 qubit quantum computer named as Sycamore, and they demonstrated that this quantum computer can solve a problem which a classical supercomputer will take a lot of time to solve. So when I say a lot of time, I don't just mean 15 to 20 minutes. I mean years or thousands of years to solve. So imagine a classical computer, the best classical computer, the supercomputer that we have will take thousands of years to solve one particular problem, and quantum computer was able to do it in a matter of seconds. So that gives us a whole idea of what quantum computing holds for us currently and the future. So if we start building a quantum computer which has, let's say, less sort of resistors, which is a perfect quantum computer, then in that case you'll find it useful for solving the problems that normal computers will take a lot of time to solve. Maybe it can find the cure for cancer. Maybe it can go through autoimmune diseases, a lot of things in all the domains ranging from mathematics to medical. Anywhere a quantum computer can be useful where normal computation takes a lot of time. So quantum supremacy has generated enthusiasm. So yeah, basically it's the same thing. By 2019, this experiment was there. And by 2020, I think around May, I got introduced to the quantum field and I went to my professor and I was like, sir, I want to do this, I want to do that. And at the same time, we had something called Qiskit Summer School by IBM. So all the things came into place for me to study quantum computing. So yeah, quantum supremacy has generated enthusiasm and interest in the field of quantum computing, driving further research, investment, and development. I think even India has significantly introduced a lot amount of money in the quantum computing field. So such a significant benchmark in the process of quantum technologies marks key milestone on the path toward practical quantum computing. Please don't go through the well. Don't record my voice because I had some cold. Okay, so moving forward, we'll need some sort of linear algebra. I promise you this is the only slide where I will talk about mathematics of it and maybe some other too. So linear algebra plays a fundamental role in case of quantum mechanics, as it provides mathematical framework for describing and analyzing the quantum system. So to represent any of the quantum states, so represent any of the quantum terminologies, will need mathematics. This mathematics is provided by linear algebra. So the computation, all the mathematics, all the notation are derived from linear algebra itself. Vector operations, and I can say the quantum states are represented unit vectors in the vector space. So vector space you can consider as a space where vectors lie basically. And these vectors are referred to as ket vectors denoted this. So this notation itself is called a bracket notation, and they represent the set of quantum system. And moving forward, you will also come across Ket-Bra notation. But yeah, so they represent the state of quantum system and contain information about the probabilities of measuring different outcomes. So moving forward, we'll see what a qubit is, what the basics of a quantum system is, how it defines a quantum state, and how it is measured. What exactly is measurement? What happens if you measure a qubit? I'll tell you all of that. But to do all the mathematics, what will require is linear algebra. So if you're studying, let's say you're studying the quantum stack, the first thing that you're supposed to study is linear algebra and then slowly move towards quantum. And then we'll again have quantum gate. So I'll go through that in the later section itself. So let's say you have a unitary measurement, unitary field or unitary state of a quantum system. And what you want to do is you want to manipulate those states. So in case of classical system, we'll have bits. So bit can be a 0 or can be a 1. But to manipulate this bit, we'll have this classical gates: AND gate, OR gate, NOT gate, NAND gate, and there are a lot of other gates. 7 to 8 gates are there. So similarly, to manipulate the quantum states, we have quantum gates, which are the building blocks of quantum circuits and are represented by unitary matrices. These matrices perform linear operations on the quantum state vectors and are essential for manipulating the evolving quantum states. So again, these gates will again be unitary matrices, which we will be applying on the quantum bits, and after applying those quantum gates, we'll get some results. So those will be the operations that will be performed by the quantum gates on a quantum state. And then again, eigenvalues and eigenvectors are important concepts in linear algebra that have applications in quantum computing. Eigenvalues represent the possible outcomes of measurement, and eigenvectors correspond to the states in which those measurements will yield definite results. So again, in case of linear algebra, we have eigenvalues and eigenvectors. In case of quantum, eigenvalues represent the possible outcomes of the measurement. So let's say you're measuring, I'll tell you what measuring is again. Let's say you're measuring a quantum state, the eigenvalues will represent the possible outcomes of the measurement, while the eigenvectors will point towards the direction of the states. Okay, that's it. That's too much mathematics for the day. Introduction to quantum computing. So yeah, quantum computing is exciting and rapidly advancing field that we have went through already, and combining principles of physics, mathematics, and computer science into one domain itself. So unlike classical computers, which uses bits to represent the process information, quantum computer uses quantum bits or qubits. So this is the first time we have came across this term. I'll tell you what a bit is. So imagine a switch. Imagine a switch which can be in the state of on or off. A switch can be on or off, but even in childhood, you must have tried this. You must have tried holding the switch such that it stays in the middle. It is not on, it is not off. So you can consider a qubit something like that itself, which does not have its own state. I mean, it does have its own state, but we won't know what state it is. Okay, so it's like you're holding the switch in the middle or somewhere over the lid, but not on zero and off. Sorry, not an on or off situation. Something in the middle. Okay, so that button or that switch in that middle position, it's called can be considered as a qubit for now. Okay, so at the heart of quantum computing is the concept of superposition. While classical bits can be either 0 or 1, qubits can exist in superposition of both states simultaneously. So imagine this. So you have the switch which is not currently 0 and not currently 1. Okay, it is somewhere in the middle. So this middle position is called superposition of the two states. Okay. So basically, the qubit can stay in the state of superposition at the same time. So it can be 0 and it can be 1 at the same time. This means that the qubit can represent multiple values at once, exponentially increasing the computational power of a quantum computer in classical one. So why this thing is there? Why this sentence is there? Increasing the computational power of a quantum computer compared to a classical one. Why does a button staying in the state of 0 and 1 simultaneously increases the power of a quantum computer, you ask, right? So imagine we are talking about only one bit. One bit can be 0 or 1. Two bit can again be 0, 1, 0, 0, 0, 1, 1, 0, and 0, 0. Sorry, 0, 0, 0, 1, 1, 0, and 1, 1. So out of the four states, when you have two classical bits, they can be only in one state. So it doesn't matter how many number of bits you have, how many number of classical bits you have. The total number of states they can take is 2 to the power n. So if you have one qubit, it can take two states, 2 to the power 1, 2. If you have two bits, it can take one of the four states, 2 to the power 2, 4 states. So it can be either 0, 0, either 0, 1, either 1, 0, or 1, 1. So among the four states, they can be either in one state. If you go further, you will have 2 to the power 3, 2 to the power 4, 2 to the power. So 8 and 2 to the power 4 is 6, 8 to the 16, 16, 3 to the power 2, 60, 64. Those sort of things will be there. So consider this. Now you have a qubit, and a qubit can be in both of the states at the same time. So as I said, classical bit, when you have one bit, it can be in one state. But a qubit can be in two states. It can be 0 or 1 at the same time. So when you have two qubits, it can explore 4 states at the same time. Okay. When you go forward, it can explore 8 states at the same time. So classical bit among the 8 states can be in one state. A qubit among the 8 states can be in any of the 8 states at the same time. I hope that is a bit intuitive. Let me know if you're not understanding. It's okay. So yeah, quantum states are fundamental building blocks of quantum mechanics. They represent possible states of quantum system. Unlike classical states, which can be fully described by their properties such as position and velocity, quantum states are described by wave functions that contain information about the probability of finding the system in different states. So again, when you have a classical bit, right? The classical bit is on and off, right? You're either passing a signal or you're not passing a signal. Okay. So you're either at that position or you're not at that position, right? But this thing is kind of like wave, so you don't exactly know where this wave is. One key difference between quantum and classical state is the concept of superposition, which we talked already, where quantum system can exist in multiple states simultaneously. Again, a quantum system, let's say let's say you have 3 qubits, it can explore 2 to the power 3 states at the same time. And using superposition, it can stay in all of those states at the same time. This allows for the potential of quantum computing to perform multiple computations at once, leading to exponentially faster processing times and classical computers. So moving back to the supremacy experiment, they had 53 qubit quantum processor known as Sycamore. So what does this mean? So this will mean that this particular quantum computer can explore 2 to the power 53 states. 2 to the power 53 is a very huge number. I mean, it is exponentially, you know, it is a huge number. So it can explore all of the 2 to the power 53 states at the same time, right? So for a classical computer, 2 to the power 53 states, you can consider if 2 to the power 3 is 2 to the power 10 is 10 to the power 3. So 2 to the power 53 will be 10 to the power 5-ish something. Those many states it can explore at the same time. Yeah. But now, since we have this qubit, we don't exactly know what a qubit is. So, or how to visualize it, right? This right side, you can see a figure which is called a block sphere. So it basically helps us understand what a qubit is, or maybe visualize it. So in the block sphere, the z-axis is basically denoted as the unit vector to pass going towards the 0 qubit, and negative z is unit vector going towards the 1 qubit. So these are the states. So this is 0, 1, and this is 1, 0 state. And all the rest of the states in between, rest of the degrees in between, they are explored using these 3 parameters, theta, pi, and psi, and they tell you where exactly the current qubit's position is. So that is why to visualize a qubit, the qubit can I'll tell you, this figure will be a better explanation to it. So see this figure, in this figure you can see that the qubit that was initially pointing to the 0th position was able to currently move towards any of the required state based on the code that you have written. So you are asking the qubit to move in a certain position, and the qubit is doing that for you. So yeah, you just change the angles and the qubit will move in all of the 3 dimensions. Right. So block sphere, I'll go through the first slide first. So this is slide 1. So the block sphere is a geometric representation to visualize the quantum states of qubit. It provides a convenient way to visualize the possible states of qubit, understand the effects of quantum operations on its state. So let's say you have applied, so let's say the qubit is currently in 0th position, and so we have to go through the gates first. Let's say you apply a negative gate to it. So what it will do is it will push the quantum qubit into the negative position to 1. It will go all the way down and come back to 1. So that is the effect of gates on a block sphere when you're visualizing. So the block sphere is a unit sphere which with the equator representing the surface of the sphere corresponding to the classical states of the qubit. The 0 state and the 1 state. The north pole of the sphere represent the state bracket 0, and the south pole represent bracket 1. The block sphere allows for visual representation of quantum operations on the qubit. For example, rotation on a qubit. The x-axis of the sphere corresponds to applying a quantum gate that manipulates the amplitude associated with the 0 state and the 1 state. So let's say you are applying x rotation, so it will rotate in the x direction, y rotation, rotate in the y direction, that sort of thing. But a block sphere helps you to visualize those things. Moving forward, similarly, rotations around y and z axis can be used. So by using the block sphere, one can easily visualize and understand the quantum states of a qubit or how the quantum operations affect these states. It provides intuitive representation that aids in the analysis and design of quantum algorithms. Again, the same thing. We have a qubit, it points towards the 0 direction. If you apply some operations on it, it will move towards the block sphere, move inside the block sphere. And the block sphere helps you understand how the movement is working. Limitations of the block sphere. While the block sphere is a powerful tool for visualizing the state qubit, it has limitations. For once, it only works for a single qubit. It cannot be extended for larger system. So if you have to look at it, look at the larger system, what you have to do is you have to put a lot of block spheres one after each other and see how it is working. I think they have came up with alternate representations for it. They can use density matrices and tensor networks to do that. These alternatives may not have the same interest. So, I mean, they're not as easy to understand as the block sphere is, but yeah, they help you with the overall understanding of the things. Okay, so I've been talking about a lot. I'm talking a lot about quantum states qubits. We'll see how exactly they are mathematically represented. It won't be a lot of mathematics. So in quantum computing, the quantum states refer to the possible states that a qubit or a system of qubits can exist in. So we can't only have one qubit, we can have more than one qubit. So when we have more than one qubit, they are called a system of qubits. So like classical bits, which can be either 0 or 1, on or off, Qubits can exist in the superposition of states, meaning they can be in combination of 0 and 1 simultaneously. So again, the button, the switch that can be on or off, can be held in between. Okay. The superposition allows quantum computers to perform multiple computation in parallel and process information more efficiently for certain type of problems. So mathematically, let's say this is your current state. This is this psi, bracket psi is your current state. And this current state is a linear combination of 0 state and 1 state, 0 bit and 1 bit, where alpha and beta are the complex probabilities amplitude and 0 and 1 are the basis state representation of the 0 and 1 states. So one here, right? And anything in between can be represented by alpha and beta, right? So again, where alpha beta are the complex probability amplitudes. These are the amplitudes. These are the amplitudes which will help you map the qubit inside the block space, you can see. Okay. Square of alpha and square of beta is set to 1. So these are probabilities. So it's either this or that, right? The amplitudes alpha and beta are constrained by the normalization condition, which states that sum of the squares of these magnitudes must be equal to 1. This condition ensures that qubit is measured. The probability of observing is either 0 or 1 is 100%. Right. Okay, moving forward. Properties of quantum states. Quantum states possesses unique properties. That's hello. Hello.
No, you can go ahead, Subodh. Someone joined newly. Their mic is not muted. Please go ahead.
Okay, sure. So yeah, so for them who have joined till now, we have went through quantum states, a bit of history of quantum computing. And quantum states possesses unique properties that set them apart from classical states. One of these properties is superposition, which allows a quantum particle to exist in multiple states simultaneously. So I've been talking about superposition. What superposition does is superposition lets the qubit exist in multiple states at the same time. So the whole basis of quantum computing, where I've told you that you can put the switch on in middle of on and off position, that position is itself called superposition. This means that a single particle can be in two different locations or have two different energies at the same time. So this switch can be 0 or 1 until unless you have actually seen what it is, which occurs when two particles become linked in such a way that state of one particle affects the state of other, regardless of the distance between them. These properties have significant implications for quantum computing and communication, as they allow for faster and more efficient processing and transmission of information. Superposition and entanglement are not intuitive concepts. So you may not see superposition entanglement in your daily life, right? It's not something you derive from classical systems, right? To have what do you call it? To have particles which can be in two different states at the same time, which is not an intuitive idea to digest itself, but it is there. And they have been experimentally verified that these ideas exist. And as superposition lets the qubits stay in two states, entanglement can see again. Sorry, I missed this definition itself. So entanglement is a property by which if you have two qubits entangled with each other, it doesn't matter how far you separate them. If you do some action on this qubit, this another qubit will be affected. So the another property is entanglement, which occurs when two particles become linked in such a way that state of the particle affects the state of one particle affects the state of other, regardless of the distance between them. So let's say you have two qubits, you entangle them, and then you separated them with millions of light years of distance. It doesn't matter how far they are, right? But if you change something in one of the qubit or one of the bit, it will do some changes in the other qubit as well, right? So these properties have significant implications in quantum computing, and because of them, quantum computing has come so far. So moving forward, however, they have been experimentally verified and are essential to development of quantum technologies. By harnessing these properties, scientists and engineers are working towards creating a powerful quantum computer, secure communication networks, and new ways of simulating quantum complex systems. Right. So again, we'll go through these concepts again. We'll go through superposition, entanglement, and measurement. Superposition is a fundamental concept in physics that describe how two or more quantum states can be combined to create a new one, right? I'm sorry, just give me 1 second. So this means that object can exist in multiple states at the same time until it is observed or measured. So we have come across this term earlier, but I'll tell you what it is. So we have this thing called Schrodinger's cat experiment, right? So what Schrodinger did was he put a cat inside a box with some poison in it. So this poison won't really kill the cat until and unless this timer is set, and this will spill the poison inside the box. Right. Now you have covered the box. We don't know what is inside the box. We just know there is a cat and there is a poison that might kill the cat. But we don't know the state of the cat until and unless we'll open the box. Okay. So let's say you have this system where you have a box where you have a cat and there's a poison inside, and you have closed the lid of the box. Now, so you don't know how the timer works. You don't know when the poison will break into and kill the cat, right? But you'll never know until unless you open the box, right? So currently, let's say the box is closed, and so this is the box basically, and the box is closed. The cat is inside the box. We don't know if the cat is alive or dead until and unless we have seen inside the box. We have opened the box, and we can see that cat is already there, right? We don't have to do anything. The cat is already there. But there might come a time that you have opened the box a bit late, and you can see the poison is already spilled and the cat is dead. So this tells you basically what a superposition is. So until and unless you open the box, the core concept is this only. Until and unless you open the box, you don't exactly know if the cat is alive or dead. So this is the famous cat experiment called the Schrodinger's cat experiment. So a third experiment in which a cat is placed inside the box with a radioactive source and a poison that will be released if the source decays. According to quantum mechanics, until the box is opened and the cat is observed, it said it exists in superposition of both alive and dead. So until unless you open the box, you don't know if the cat is alive or dead. So this illustrates the bizarre and contradictory nature of quantum mechanics. Quantum mechanics again, right? So again, to put it simply, flipping a coin. Before you look at it, so let's say you have flipped a coin, it is there somewhere on top of you, and you haven't looked at it, you don't exactly know which state it is. So until unless it comes back into your hand and you look at it, you don't exactly know if it is heads or tails. So before you look at it, the coin is both heads or tails at the same time. It's only when you observe that it settles into one state or the other. This is the basic example of superposition, right? So again, quantum superposition. Superposition is a fundamental principle in quantum mechanics that allows quantum systems such as qubits to exist in multiple states. Now we are mapping the concept of quantum mechanics to the concept of qubits, right? So qubits we have studied earlier. Qubits can be in state of 0 and that is what I said. So the sentence where I say that a quantum qubit can be in a state of 0 and 1 at the same time comes after superposition itself. So like classical system, which can only be in one definite state at a given time, quantum system can be in a combination of superposition of different states. So in context of qubits, a qubit can exist in a superposition of 0 and 1. Mathematically, this is represented by quantum state vector that combines the probability amplitude associated with each state. So let's say this is psi, and the psi can be in state of 0 and 1. So this is single qubit system, right? The single qubit can be 0, can be 1 with some given probabilities, right? These probabilities, as I've told earlier, are represented by alpha and beta, alpha square, beta square giving to 1, right? So this is how mathematically it is written. So psi can be in state of 0 with probability alpha, and beta can be in state of 1 with probability vector beta, right? So alpha beta complex probability amplitudes that determine the probability of finding the qubit in either 0 or 1 state upon measurement. Measurement is the same as opening the box and looking at the cat. The magnitudes of alpha and beta represent the probabilities, and their phases determine the interference pattern that arrives when multiple superimposed qubits interact. So alpha and beta will basically tell you the magnitude, how much of how much of the qubit, how much of psi is in 0 state, and how much of it is in beta state. So that is what we call the phases of the qubit, right? So qubit can be in 0 or 1, but psi, alpha and beta actually tells you how much of it is in 0, how much of it is in 1. Example, one common example of superposition every day is the phenomenon of interference of sound waves. When two sound waves with the same frequency intersect, they can either reinforce each other or cancel each other out. And depending on the relative phase, this is why you might hear loud noise when standing between two speakers playing the same song, but almost no sound when standing directly in front of one of the speakers. So to do this, I can give you a small example. What you can do is you can take your phone, play the same song in both of the phones and put them right here, right? What it will do is the sound waves will come together and give you a louder noise as compared to just one speaker. But at the same time, we also have noise cancellation headphones. So how noise cancellation headphones work is you put on the headphones and it looks at the frequency of sound that is coming from outside. It generates a negative frequency to it so that whatever frequency comes to your ear neglects. So it goes to zero. Right. So that is how superposition basically works. Another example of superposition can be found in quantum mechanics, where particles can exist in multiple states simultaneously. For instance, an electron can exist in two different energy states at once until it is observed and collapse into in a single state. This principle underlies many of the strange or counterintuitive properties of quantum mechanics. So superposition technology, one of the most exciting applications of superposition is in the field of quantum computing itself. By utilizing the ability of qubits to exist in multiple states simultaneously, quantum computers can perform certain calculations exponentially faster. This has the potential to revolutionize fields like cryptography, drug discovery, and even climate modeling. So again, these are the fields where you'll require you'll have to explore a lot of states in a very short amount of time. So think about cryptography in such a way. Cryptography has block ciphers and everything, right? So these ciphers, you have to make them in such a way that nobody will be able to hack them, right? So you build them with quantum computers, you build them with qubits, and you don't exactly know how this is, but at the same time, they can be measured at the entry point of it and the exit point of it. So they can be helped. Drug discovery, again, some example include cancer treatment and everything. Right. In addition to quantum computing, superposition also plays a key role in modern cryptography. For example, quantum key distribution is the principles of superposition to create unbreakable encryption keys, as I've said just now. By encoding information into quantum states of particles, it becomes impossible for eavesdropper to intercept the key without disturbing the system. So to give you a basic example of it, let's say you have sender and you have a receiver, and the sender has encrypted the key in 30 qubit system, so it has explored 2 to the power 30 states, and only the receiver knows how to decrypt the key, right? But let's say I'm an eavesdropper in between them, and for me to understand what exactly is the key, I will have to go through I will have to go through 2 to the power 30 states at once. So for a classical computer, going through 2 to the power 20 states is nearly impossible task. It will take a lot of time. So if it takes a lot of time, the whole purpose is disturbed, right? Purpose is nullified. You want it to be done faster. So that is why quantum computing can be used in cryptography. It will be a very beneficial thing for cryptography itself. So yeah, moving forward, now we know what a qubit is. We know it can be manipulated, measured, and everything. But to manipulate this qubit, what we'll need is we'll need the gate. We'll need gates. We'll need something that will manipulate the qubit to perform some operations. So in the image, you can see these are the normal classical gates that we have: AND gate, NAND gate, OR, NOR, NOT, XOR, and XNOR. These are basic basic classical gate that you are seeing in normal mathematics, design systems, and everything, right? So similar to these, what we are doing is we are building quantum gates. I mean, not me, but we have quantum gates that will be applied on quantum systems or quantum gates to manipulate them, right? So quantum gates are building blocks of quantum circuits. They are analogous to classical logical gates, but operate on quantum bits or qubits instead of classical bits. So like classical gate, which can only output 0 or 1, quantum gates can output a superposition of states, allowing for exponentially more computational power. So in quantum gates, if you are putting a vector, it will give you back a vector basically. If you put one state, it will give you one state. If you put a vector, it will give you a vector. If you put a matrix, it will give you a matrix. So quantum gates can output superposition of states. One key difference between quantum gates and classical gates is the quantum gates are reversible. So this means that the input can be recovered from the output. So Classical gates, if you apply 0 to 1, maybe sometimes you get the 1 back. But in quantum, you can definitely get it. Another difference is that quantum gates can easily act on multiple qubits at once, whereas classical gates can only act on 1 bit at a time. Okay, so there are in general three types of quantum gates: the single qubit gates, 2 qubit gates, and multi-qubit gates. Single qubit gates operate on single bit, as the name suggests. So this gate X, Z, H, T, these are all the single qubit gates. 2 qubit gates, as the name suggests, operates on 2 qubits at the same time. They can entangle the 2 qubits, meaning that their states can become correlated. So even to put two states into the entanglement, we have to use 2 qubits. Examples of 2 qubit gates include the C0 gate, which flips the second qubit if the first qubit is in state 1, and the swap gate, which exchanges the states of the 2 qubits. So yeah, these are the 2 qubit gates. And multi-qubit gates operate on more than 2 qubits at the once and are used for more complex operations. One example is the Toffoli gate, which performs a controlled NOT operation on 3 qubits. These gates are essential for performing large-scale quantum algorithms. So again, these are the mathematical notations for the different types of gates we have. And this in the GF you can see, this is basically happens. So if you have 0, if you put gates on it, will go. And currently it is 0 state, so nothing will really happen. If you put a Toffoli gate over here, you'll get something like this, and the C0 gate here, and X rotation gate and X rotation gate in negative direction. These are the, if you put operations on a normal qubit, these are the things that will happen to the qubit and they will change the states. As you can see, using the block spin, it gets very easy to look at the states of the qubits. Right. Entanglement. So moving forward, we'll see what entanglement is. Entanglement is a fundamental concept in quantum mechanics where 2 or more particles become correlated in such a way that the state of one particle is dependent on the state of others, regardless of the distance between them. I told you this earlier, what entanglement is. These particles are said to be entangled and their behavior cannot be described independently, but as a combined system. So again, let's say you have 2 qubits, they are currently entangled in, and put them at a certain distance or any distance for that matters. And this thing, whatever operations you perform with one qubit reflects on the other qubit. And this whole thing cannot be represented separately. You can't represent qubit 1 and qubit 2 separately. This whole thing will be considered as a complete system, right? So when particles become entangled, the quantum state of system as a whole cannot be decomposed into separate states for each individual particle. Instead, the state of the system is described by a joint state that encompasses all the entangled particles. The entangled state cannot be expressed as a simple combination of the individual states of the particles. So once they are entangled, you can't really tell that this qubit 1, I am measuring this only. You cannot do that. You have to measure the whole state and get the results out of the whole state. It plays a crucial role in quantum computing and quantum communication. In quantum computing, entangled qubits can be used to perform operations that exploit their joint states to achieve computational advantages. For example, entanglement is a key resource for quantum algorithms like Shor's algorithm for factoring large numbers and Grover's algorithm for database search. Again, these are some of the algorithms. You can go read about it. Shor's algorithm is extremely famous, and Grover's algorithm provide a very faster way to access keys inside a database. Grover's pre-search algorithm, you can call it. Entanglement also has implications for understanding of nature of the reality and concept of measurement in quantum mechanics. The phenomena challenges classical intuition and suggests that quantum systems are fundamentally interconnected in ways that go beyond the classical understanding of cause and effect. So we have discussed this earlier. These phenomena, entanglement, quantum computer, is not intuitive. So it's not something you can you work on your daily basis. It's not something you work on daily basis. It's not something you encounter in daily basis. So these formulas, as they are verified, they can tell us a lot. Yeah, moving forward, quantum measurement. So as I've told you, right, the cat is still there inside the box. We haven't opened the box yet. So to open the box is to measure the state of the quantum system. So cat being in the state of dead or alive is the quantum system, and to open the box is called the measurement of it. So quantum measurement is a process of quantum mechanics where the state of quantum system is observed or measured to obtain the information about its properties. When a measurement is performed, the quantum system, it causes the system to collapse into one of its possible eigenstates, yielding a definite result. So we have the cat inside the box. We know that there is poison inside the box, but we don't exactly know if the cat is dead or alive. So the moment you open the box, you can see the cat if it is dead or alive. So that is what it means. So when measurement is performed on a quantum system, the cat here, it causes the system to collapse. So after measurement, you can exactly see if the cat is dead or alive. That is the crux of quantum measurement. Quantum measurement, again, is a crucial aspect of quantum computing and quantum information processing. Measurement allows us to extract information of a quantum system and obtain the results of quantum computation. They are also essential for encoding and decoding quantum information and quantum communication protocols. So again, you have this whole quantum system. You have, let's say, 2 to the power 53 qubits in a quantum system, and all of the qubits are exploring different states, right? But you don't exactly know what is the state of the quantum system until and unless you have measured those qubits. Understanding and controlling quantum measurement is a key challenge in quantum technologies, as the measurement induced disturbances and coherence can degrade the performance of quantum systems. So what this basically means is, first of all, creating a stable qubit is a very difficult task. And after that, measuring the qubit is even difficult than that. We have a lot of natural things that we have to work out. See, currently we are only talking about in terms of mathematics and quantum computing, right? When it comes to the actual physical part of it, physical counterpart of it, we have to actually build a qubit which can stay in the state of superposition and which can react to the operations that we are performing on the qubit. And then we have to measure the state of the qubit. So let's say in case of classical, again, I've told you, classical system is just you are passing electricity so through a system, or you're not passing electricity. So that is 1 or 0. But think about it this way. Can you really think about something, think about a state where you can put the material of 0 and 1 at the same time. So in general, creating a state of superposition or creating a qubit itself is a difficult task. And on top of that, measuring the qubit to collapse it to one of the possible states, it's even humongous task. So that is why, as measure-induced disturbances and decoherences can degrade the performance of quantum systems. So when you're measuring the quantum system, can have a lot of difficulties in the measurement. The measurement may not be accurate, or some natural factors can come in and disturb the system. Disturb the system itself. That is why researchers are actively working on developing techniques that to mitigate these effects and improve the accuracy and reliability of quantum measurements. So in general, what I have worked on is simulators of quantum computers, right? So what simulators are good for is there are no physical aspects to worry about. You know that this is the system. If you apply this part, you'll get this as a result. But in case where physical parts come in, you have to worry about a lot of things over there. That is why researchers are actively working on developing techniques to mitigate these effects and improve the accuracy and reliability of quantum measurements. Right. So we are kind of moving towards the end of it. Now, we have these things in our hand. We have superposition, we have qubits, block sphere, we have measurement, we have entanglement, all of those things. How to use those things? So there are a lot of algorithms that are generated by a lot of different people, and these are either basis of quantum computing, you can say. And since the evolution of these algorithms, a lot of people are interested in quantum computing itself, and they themselves are developing a lot of quantum algorithms. So we kind of started with quantum teleportation, basically. So computational procedures. So quantum algorithms are basically computational procedures specifically designed to be executed on quantum computers, and the unique properties of quantum system to solve certain problems more effectively than classical algorithms. So these are the algorithms, you can say, which performs better on a quantum computer compared to classical computers. So yeah, I basically have to start with quantum teleportation that allows the transfer of exact quantum state of one particle to another particle without physically moving the particle itself. So let's say you have two particles here, right? And what you want to do is, so think about it this way: can you have two things in the universe? Can two things exist in the universe with exactly same properties? So can another Subodh Bijwe exist in the universe with exactly same properties? No, right? There can be only one thing with exactly same properties. In this case, in case of human, the properties can be history of the human, maybe his heart rate, maybe the way his brain is wired, all of those things. So think about this way: no two systems in the universe can exist exactly in the same thing, right? So that is the root of quantum teleportation. It says that we basically have no cloning theorem. So no cloning theorem basically states that you cannot clone a quantum state, which in turn transforms to no two states exist in the universe with same probabilities. So that is why to teleport data from one state to another state, we are not teleporting the state itself, we are teleporting the data from one state to another state, or maybe state of one qubit to another qubit. So allows the transfer of exact quantum state of one particle to another distant particle without physically moving the particle itself. So you are not moving particle from position 1 to position 2. You are moving the state of particle 1 from this position to another position. Right? I hope that makes sense. So similar to quantum teleportation, there are a lot of algorithms. One of the major algorithm that was the breakthrough was Shor's algorithm for integer factorization. And then we again have Grover's search algorithm, quadratic speedup of searching an unsorted database compared to classical algorithms. So again, this thing I have mentioned earlier, you are looking for something inside a database, and the Grover's algorithm helps you find it in a very less amount of time. I think it is order of log n time, if I'm not wrong. But then Grover's algorithm uses a lot of other algorithm called quantum Fourier transform, basis for many quantum algorithm, including Shor's algorithm. And quantum simulators leverage the ability of quantum system to model and simulate physical system at quantum level. And variational quantum algorithms where we combine the classical and quantum processing to solve optimization problems. Right. So the future of quantum computing. The future of quantum computing holds great potential for advancement in various fields, solving problems that are currently intractable for classical computers. So first of all, classical computers are fast. Classical computers are extremely fast. We have supercomputers that can do a lot of processing. Even single Google search takes a lot of time for a supercomputer to process, but it does it very fastly, right? So now we have to look at the problems which are definitely hard for a classical computer to solve, and then we have to look at how we are going to leverage the quantum computer to solve the problem. So while quantum computing is still in very early stages, ongoing research technology developments are paving the way for significant progress in the coming years. So what I have explored is the field of quantum machine learning. So we are trying to build quantum machine learning model to process the data or to perform machine learning using quantum computers. It's a very huge thing again. But we have to look at the problem which cannot be solved by classical computers and can be systematically programmed on a quantum computer to be solved, right? So some of the fields I have mentioned here are quantum simulation and scientific discovery. Quantum computers have the potential to simulate and model complex quantum systems that are difficult to study with classical computers. So how else will you have 2 to the power 53 states in a classical computer at the same time, right? A classical bit cannot explore those many states. That sort of thing. So the capability opens up to avenues for advancements in fundamental physics, chemistry, material science, allowing research to explore new materials, understanding quantum phenomena, and make scientific breakthrough. Hybrid classical quantum system. In near term, hybrid classical quantum systems are expected to play a significant role in quantum computing. These systems combine classical computing resources with quantum processors to leverage the strength of both paradigms. Hybrid approaches can help mitigate the limitations of quantum system and facilitate the development of practical applications and algorithms. Why this is important? You say, let's say we have machine learning problem. What we want to do is we want to classify if a number is even or odd, right? Or maybe classify images. And so we have given images, so I have to see which numbers are written there in the images. So MNIST database is there. So what we want to do is, so MNIST is a classical data. It's not a quantum data. So there are 4 fields in it basically. We have classical data with classical system, classical data with quantum system, quantum data with classical system, and quantum data with quantum system. So the data that we already have in our world is classical data, right? And what we want to do is we want to create quantum algorithms. So we have to build a system which can incorporate both classical and quantum fields and then produce results. Because we even if you're moving to a future where there is a lot of quantum usage, we have to migrate our whole classical databases to a system which will be which will use quantum to do those things. So that is why when we move towards a quantum system, we first have to go through the hybrid of classical and quantum systems, and then quantum networking communication. So quantum communication is an emerging area with the potential to revolutionize secure communication and information exchange. The process of quantum computing involves the development of quantum networks that connect quantum computers and quantum devices, establishing distributed quantum processing and secure quantum communication protocols. So I have given you an example of quantum cryptography where you have a sender and a receiver, and there's an eavesdropper in between. So it gets difficult for the eavesdropper to understand what data is being passed from one end to other end until if the data is being secured through a quantum channel. So networking, moving forward, let's say we have an internet which is constantly built on quantum things, right? Quantum networking, and you're passing data through quantum system. So even the voice that is going through the internet itself. But if it is being passed through a quantum system and you guys are the receiver of it, I will be sure that the data is properly secured and nobody else will be having access to the data, right? So yeah, these are some of the fields. There are a lot of fields where you can use quantum computing, and a lot of people are already trying that as well and being successful as well. Yeah, that is all from my end. Let me know if you have any questions.
So now Q&A open. Anyone have any question? Please feel free to ask in chat window or unmute yourself, ask question. Okay.
Sir, currently working as an academic mentor. So I wish to do a research work related to this quantum computing online. I wish to do a work online, a research work. So is it possible to do so?
Yeah. I think IBM Quantum is already giving you quantum capabilities. You can use their quantum simulators or maybe quantum computers to do your research. I did that.
So, like, can you please say about any kind of research works that I could do?
Any sort of research work that you can do. What are the things that you're exploring, first of all?
Currently, I'm in love with quantum computing, but I have a lot of doubts regarding that. Like, what topic, what might be the questions that I should solve, like that. So I do not have a mentor right now regarding this topic.
Okay, you can think about it this way, right? What you want to do is you want to create a quantum algorithm to solve a problem, first of all. Then you have to look at the
Okay.
problems that the classical computer is solving already. And then say it's okay if you don't make a breakthrough. We don't really want a breakthrough. So let's say you are doing some basic task like maybe creating a calculator. But if you can create the calculator using a quantum system, that is also research, right? We're moving step by step forward. So think about the problems that the classical computer is already solving, and think about how we will generate an algorithm through which the quantum computer can solve the problem. So you basically have a classical algorithm, you map it to quantum system, and you create a quantum algorithm to solve it using quantum computers.
Okay, sir,
Does that
that's
make
right.
sense? Hey, you don't have to call me sir, you can call me Subodh.
That's nice. Any other questions? Great.
Yeah,
Okay.
I have a question regarding the
Yes,
ket
please.
bra vectors. What do they actually signify? Why are they used here?
Think about it this way. So in case of classical systems, you have 0 and 1, right? And these things are used to identify basically on and off situations. So think about this, you're building a computer and what you want, the basic of everything is just 0 and 1. So in case of quantum, the basic of everything is the 0 and 1. And to make them different from classical system, you're putting bracket on top of it. So when you're putting
Hello.
Did we lose Subodh?
Yeah, looks like we lost.
Sorry.
Yeah,
Hi.
he's back. I think
Okay,
Subodh
so
is back.
Yeah.
I thought I was talking to myself then.
Subodh, we lost you a few seconds.
Okay, sure. No issues with that. See, think about it this way: you are building a computer, and the basis we want to do is we want to build a quantum computer, and the basis of quantum computer is the 0 bracket and 1 bracket. So the what do you call it? The basic thing, the unit of measurement or the unit thing, you can say the core thing of everything, just for the representation purpose, we are putting 0 and a bracket on top of it to differentiate between the classical system. So 0 is a vector of 0, 1, and 0 bracket is a vector of 0, 1, and 1 bracket is a vector of 1, 0. I can show you, just give me 1 second. I think let me just Wikipedia those things for you.
I will share. Okay. I will
I'll
share
share
the
my
screen.
screen.
Okay, yeah, please.
Hey, if you want, you can do it, KJ. I don't have a problem.
No. Go ahead. Go ahead. He explained with that. You're good at that.
Okay, I think I shared the wrong screen.
Yeah, you share the entire screen.
No, that's okay. Can you see the screen?
Yeah.
Yes, sir.
So if I just zoom in, this 0 is a vector of 1, 0, right? And this is a vector of 0, 1. So they basically tell you the state of quantum things. And the only difference you can say from classical thing is just representational part of it. You can directly write 1, 0 and 0, 1. We will understand, but for the easier sake of it to write it to the mathematics, so every time you will not be able to write 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, right? For that, you are just representing it into the bracket notation. That's it. Vivek, does that answer your question?
So Vivek, that helps
Or
you.
there is quantum disturbance. What? 2 power 53
Our
state things. 2 power 53
53.
states. So think about it this way. So 2 to the power 0 is 1. 2 to the power 1 is 2. 2 to the power 2 is 4. 2 to the power 3 is 8. So if you move in that way, 2 to did you lost me again?
No. We are hearing.
Achha. So similarly, 2 to the power 53. It's like 2 into 2 into 2 into 2. There are 52 2's over there. So that is what 2 to the power 53 statement. So I don't think anyone can calculate that.
And I think Dhaval is want to know what is the significance of the number 53. Am I right, Dhaval? Dhaval, if you know, you please unmute and then explain, because I believe that you know the significance of that number 53.
No, I just wanted to look at understand the problem of 2 power 53 states. In the beginning, we started with one of the problems, right? So I know that what 2 power 53 is. Just that.
So mathematically, we can easily understand, but the
I
number
just want to
53
know.
connotes the number of uh, addressable, what is called, it is these some quantities there. 2 power 53, 2 power 253, 2 power 1000, something like that. The number of states or number of atoms, the number of known elements in the known universe, those kind of thing.
I think I have heard this analogy as well. 2 to the power
Yes, I
50 is
forgot
equal to
that exactly
the
it is 2 power 53.
total number of grains of sand in the whole on whole
Yeah,
something like that.
yes,
I heard the
something like
analogy.
that.
But see,
So
again,
Yes.
I'm not sure about it. So
So
actually,
I'll
that
just go
number
and count
53
and
are
confirm.
associated with a certain count, because when you are
I
talking about the qubit, they will use certain number. Why they selected 53? Because that connotes certain number of elements. I heard that when we have 1000 qubits, we will be able to address certain quantities, something like that.
there's no, I mean, I don't know if there is significance of it, to be honest. I just know the
no
research.
worries.
That's it.
No, I'll
There
just
is
go
a
and count the sand particles
Dhaval, you
and
can
come back
find it
and
and then
confirm.
share it. Okay. Any other questions? Team, feel free ask questions, because this is very interesting to see. It is a mathematics, but purposefully Subodh prepared with less kind of formulas and all. such that you feel more comfortable, because a lot of mathematical expressions, considering the audience level, may get lost. That's the reason why he
No, we
prepared
just
and then
wanted everyone
explained
to
very
be
well.
on same page, basically. Just want everyone to be on same page. Moving forward, maybe you can have a lot of sessions where mathematics is involved.
No more questions? Okay. If no more questions, I will continue with certain explanation to the mathematics, such that that will help you to this is will, in addition to whatever Subodh explained, I'm going to explain now. I can't promise that I will have text. This is going to be formula. Let me share my screen and then go with uh, the session what we have prepared in continuation to that one. Hope you are seeing my screen.
Okay.
Yes, KG.
Yeah. So I want to start from very basic. We know that what is this one? This is the classical computer, either laptop or desktop. If you open this one, you will see um, drives, CD drives, or if it is a old system, and then there will be a motherboard, right? Motherboard is the important part of the uh, digital system, any classical computer. Inside motherboard, we will have microprocessor. If we want to go inside microprocessor, what will you see? It is we never in normal level, or people who are not computer architect or more into digital electronics, they never go deeper into that one. But if you go deeper, you will see this circuit board or arithmetic logic unit, ALU, control unit, registers, memory. This is the architecture. Now, if you think about how this architecture is performing the calculation, just now Subodh showed 2 into 2 into 2 into 2 into 2 power 22 power 53, it is showing a number. If you're performing some other calculation, it is giving the correct result. If you are searching for a record, it is searching. So how this digital system is able to do those mathematical operations? If you think about that one, it may kindle some interest, or you may want how this is possible, because this is 0 and 1, as Subodh just now told, binary digit, zeros and 1. But how zeros and 1 is able to show a image, how it is able to search a record, how it is able to do ATM transaction, how it is able to machine learning, artificial intelligence, chat GPT. If you think about those things, you will land up something called Boolean algebra, binary numbers, bit and or operators. These are the things built inside the digital computer. Like, see, this is the accumulator. If you see here, this arithmetic logic unit, that ALU has a component called accumulator. That accumulator again have a component called adder. That adder is built using this XOR gate, AND gate, OR gate. It is a input one bit A and B, then we'll get some, then we will carry out. That carry out is fed to next to full adder as the input, which is C in. So now you will realize this kind of binary or electronics gates, digital electronic gates are used to perform whatever we are doing in classical systems. In 19 not 19, in 18th century, Charles Babbage was telling that the machines can perform mathematics or calculation. No one believed him, because the technology is not matured that much level what he is expecting. But in 1980s and even 1960s itself, we had a digital computer, right? A kind of semiconductor, vacuum tubes, those things came. Something similar to this is happening in the quantum computing also. We are in that stage. Now we are seeing, that is the reason why we have to understand mathematics. So what is the basic difference between mathematically? What is the basic difference between classical and quantum? Classical systems are operating Boolean algebra and are not gate, something like that. Whereas linear algebra is operating on, quantum computers are operating based on linear algebra. and here it is binary numbers, but here it is complex numbers. That is the reason why when Subodh is telling that it is zero ket, what is the meaning of zero ket? Certain portion of 0, certain portion of 1. That's why the ket notation. Vivek, you asked a question, right? Why we have to put into ket? So let me, I have to go to, let me open Paint. So when you have 0 and 1, this is what actually one data in quantum qubit. So how can we, every time I can't write like this, right? So I will put one ket. In ket notation, the bottom value is represented here. If I want to represent 0 ket, it will be, this is this
Karthik, you're not
vector.
able to share that paint is not seen actually.
Oh, my bad. Sorry. Let me stop sharing and then share my entire screen. Thanks for pointing out because this paint is very important because this based on my previous sessions, I realized this particular example helped most of the people. Why this ket notation? So instead of this big vector, I'm conveniently representing using this ket notation, and it was introduced by Dirac. So the Dirac is a scientist working on the atomic research center. Dirac, Niels Bohr, Schrodinger, and Einstein, Max Planck. Max Planck is senior. These are all contemporary people. They used to communicate during the, you remember 1921 conference. During those period, prior to that itself, Dirac explained this Dirac notation. He presented this Dirac notation for atomic number representation because those states are complex number. That is the reason why he proposed a convenient method to represent these complex numbers. So that is how that mathematical models start building for quantum computing. So if you remember these three things, linear algebra, complex number, and qubit, that will help you a lot. Because of the complex number and an algebra, now you remember Subodh told these are all reversible gates, meaning that the number of input line and the number of output line are always same. That is the meaning of that one. See, in AND gate, we have two inputs, one output, but all quantum gates are equal numbers. Two input, then you will have two outputs. See, for Rx, Ry, Rz, you will have two inputs. If it is Cx or CCx, you will have three inputs or four inputs. That kind of reversible gates concept are employed in quantum computing because of this linear algebra, complex numbers, and they are giving you the capability to generate the input from the output. So now after explaining all those things, you will little bit go blank. What does it mean? So here I will take a pause, answer your question, then continue. Any question? Feel free to ask the question.
Sir, in between, can I say something?
Yeah, please. Yes, Christy, please go ahead.
So I wish all the participants, I request all the participants to on the camera and let's take a group photo.
Yeah, that's good. Thank you. Yeah, please, everyone switch on the your camera. We will take a
Group photo.
group photo. That's great. Yeah, Deepa, Pradeep. Morani. Aftab is there, right? Vivek, thank you. Thanks for coming online, coming on video, camera. That's great. That's great to see. Deepa, have you taken screenshot? Christy, are you taking?
Thank you.
Yeah. Good. Any other question? I'm open to question to answer your question on how this fundamental mathematical foundation, because next we are going more complex explanation. Yeah. Cool. Can we continue?
Yes, you can continue, KG.
Yes, sir, we can continue.
But unknowingly, I closed that PowerPoint presentation. Let me stop sharing my entire screen. Okay, it may be record. Maybe record. So usually, this one slide I always like. This is quantum computing. This is astounding. So anyone remember from which movie this scene came? This particular, anyone who are attending the session can recall this one? This is from the science fiction Transcendence. And Johnny Depp, you can see the Pirates of Caribbean in a different avatar in this movie. He transformed his consciousness into a computer. Then that computer will behave like him. Then that conscious will build a quantum computer. So this is that quantum computer. What they are seeing now, this is the quantum computer in that movie. It is one of the amazing movie. If you are able to see that movie, that story itself, amazing story. So I encourage. I don't know whether it is available in any of the. I did not see in Amazon Prime, but it might be available in one of the OTT, or you will be able to download. Watch this movie. That will give you a good weekend movie watching experience. So this is one thing in that movie. They have talked about few of the quantum computing properties, but now we are focusing on mathematics, right? Let us come back to the complex numbers. This is the complex numbers. So that I believe all of you or most of you remember this I square equal to -1, right? A complex number z equal to x plus iy, and it has two components, real and imaginary. And this iota, e power iota, see the e power iy, it can be written as a complex number in terms of cos, cosine and sine, using cosine y plus I sine y. So this particular expressions are helping us to understand the real and imaginary part. And this diagram, what is called Cartesian coordinates, it helps us to understand how a complex number can be represented both Cartesian coordinates as well as polar coordinates. So when people are discussing about vector and then associated linear algebra operations, the first thing will come to our mind is the speed of car, or very fundamental formula, fundamental mathematical problems, right? But when we add a complex number element to this standard real linear algebra, see, assume that linear algebra is an operation. You can perform vector, matrices. These are the standard operations. You can put integer or real number or complex number. Am I making sense? So you imagine this way. You are determining, assume that you are in Majestic railway station, KSR railway station, you are boarding a bus to Mysore, sorry, train to Mysore, and that train is moving at a constant speed towards west direction, then it will reach. So that can be represented conveniently using a vector. Am I right? Some x coordinates, y coordinates, or angle with the speed, we can conveniently represent. This is easy problem. Now imagine that you are going subatomic scale. Subatomic scale means I am talking about the electron. The electron is having a spin. That spin is not normal rotation spin. It is called IAM, intrinsic um, uh, intrinsic angular moment. So intrinsic angular moment is a rotation which cannot be measured with a real number. There will be always some imaginary portion. That is the reason why we need complex numbers for quantum computing. Am I making sense here? Here I would like to take a pause, answer your questions. So complex numbers, understanding of the complex numbers are very, very important for understanding quantum computing states, all those things. Are you ready to answer your questions? The complex number, it's complicated concept. Uh, it is not easy to comprehend how a complex number representing a known behavior or something like that. Because a train going to Mysore, we are able to visualize or imagine. But when I'm telling that the spin of an electron in terms of intrinsic angular moment, we cannot imagine because we never had a chance to visualize or discuss about the quantum spins. Only the physics with the masters or PhD level, they only used to discuss. Even during our college or school studies, we have not had a chance to go into that level. But these days, there is a quantum mechanics, one of the subject. The current generation of students are reading. Can you please share if any links to learn more about linear algebra? Yeah, yes, I will share. Subodh, can you find some link and then share if possible? Otherwise, I will share because I
I
know
will
best
tell
of
them.
linear algebra.
I will tell them there is a god of linear algebra, and they
Please
can
go
go
ahead.
and follow them. I'll share them. I'll share them.
Yeah. And personally, I like to watch the YouTube video 3 brown 1 blue, 3B 1B. If
3
you
blue,
search,
1
go
brown.
to YouTube. 3 brown 1 blue, right? Or 3 blue 1 brown.
3 blue, 1 blue, I guess.
Okay, 3 blue
I'll
1
give
brown.
the links. Don't worry. You continue, Kelly. I'll give the links.
Okay. Personally, I love that 3B 1B. That's a great source. And Khan Academy also good source. So you can learn from there. So now from this explanation, I'm moving to Bloch pair. Why Bloch pair? See, if I every time if I write like this, you cannot visualize a quantum state because quantum state is a it is a n-dimensional Hilbert space. Again, another jargon, Hilbert space. Don't worry about that one. That kind of Hilbert, any component or any behavior happening inside the Hilbert space cannot be represented using the 2D. That is the reason why we are going for a 3D Bloch pair. Subodh demonstrated with a beautiful image that will help you. I want to go back to that. Yeah, this one. So for that, I have to show us a slideshow, right? Then only it will appear.
Yes.
You see here. You see, it is there is something moving, right? Actually, there is no any arrow, but the point what is moving, that is the spin energy. We can consider, we can visualize this as a spin energy. So now, if you are able to measure the spin energy, voila, you have it will a Pandora box opening, meaning that for example, 3 plus 7. We know 3 plus 7 equal to, 3 plus 7 equal to 10. We know that, right? Imagine that 0, 3 is one vector, 7, 0 or 0, 7 is another vector. If you are able to put this 0, 3 into one qubit and another 0, 7 into another qubit, and if you are performing vector addition, mathematically we know, right, it will be 0, 10. So you know that is 10 ket. How that can be represented is a Bloch pair. Just give some electromagnetic wave such that the spin energy or IAM of the particular electron is moving to one position, which we can consider as a 3. Then another movement, it will go to 7. If you measure now, that will give you 10. Actually, it is not happening in the real quantum computing. It is happening something deeper. To make sure that you are understanding mathematically, I'm coming down with a very, very how to say, layman explanation. If you are able to visualize this, you will understand how quantum computer are able to perform some mathematical operation. Am I making sense now? I would like to take pause here because this is one of the important concepts. If you ever want to understand quantum computing in higher level, this particular understanding is necessary. This particular visualization by Subodh, it is amazing explanation of or demonstration of how a Bloch pair is performing some operation. And you can see here it is happening only the sphere. That's why it is called unit. You might have seen one expression I will show now. That layer, outer layer, is very, very important. Cool. Any question? Looks like no question. Let me go back to this particular state vector or represented on the Bloch pair. And these transformations cannot be done with the standard arithmetic operations. They must be done with the vector operations. Here the vector are not just vector, they are matrices. Those matrices must be Hermitian matrix because they are conjugate transpose, which will make sure that the operations are always on the sphere, not inside, not outside. Then only we will be able to measure the outcome. That is one of the understanding or assumption, but it is actually, it is a constraint. If you go out of the sphere, you have a lot of capabilities, but that is not possible with the current technology. That is the reason why they limited to a unit, a Bloch pair, which is represented by a unit vector or the number a square plus b square equal to 1. That or magnitude equal to 1. Any question here? No question? That's interesting. Okay, cool. Now I would like to explain the theory part of state vector and transformation. So these two mathematical concepts are employed in quantum computer such that the quantum computing operations are mathematically defined. See, any system, any computing system or analysis system, whether it is analog system or digital system or special purpose system or general purpose system, their states must be clearly defined by a mathematical model. Usually it is given by finite state automata, FSA, or finished state machines given by Turing machine. Turing machine is the mathematical model which will give the states of any system. For example, if you take a bus, the bus will be the stop. It will be what is called halt state. Then it will start state. Then move state. If something happened, crash state. These are all well-defined states for a moving vehicle. Like that, a digital system will have multiple states. Like that, a quantum computer also will have a state. So for car or moving vehicle, we can write in a paper with the number of states in the string. For digital system, these are all binary states. That's the reason why we have 0, 0, 0, 0, 0, 1, 0, 0, 1, like that, the binary numbers or hexadecimal number. That's what we use to represent the states of a digital system. Similarly, we need a mechanism to mention the states of quantum system also. Being the quantum systems are a complex numbers in Hilbert space, we cannot use these kind of notations. That is the reason why we have a special notation called ket notation. That ket notation is nothing but a way to represent the vectors. Since these are all vectors, those states are represented with the vectors. It looks like it is making some sense, but if you close your eyes and then try to think about, oh my god, I'm not able to follow, don't worry. This is how the quantum computing, the mathematics for quantum computing looks like at the first attempt. Subodh, how many times you gone through the mathematical concepts over a period of time to understand, to get the clear picture?
To get the clear picture, I don't know, maybe 10, 20 times. It's still going
Yeah.
through, I still don't know.
I have gone through more than 20 times, 50 times, because most of the time I used to think through during the travel, or after reading the book, or after writing on a paper. I used to think how this is happening inside an electron, or inside the photon, or when the photon is transmitted, how these things are happening, how they are noting down that value. So I went down a low level example, try to understand a photon transmission like the bullet train is traveling. So a bullet train travel and photon transmission looks like, oh, what kg, why are you comparing uncomparable things? But for me to get an idea, I tried to think, then I realized bullet train never had this single photon kind of behavior. It cannot tilt. It don't have polarization, right? Something like that. Then I realized, no, photon must be think through as a photon only. Electron must be think through as an electron only. That is how I realized multiple attempts thinking. So this is very, very essential to get a proper understanding of a quantum computing. So rather than reading, if you read for 5 minutes, I recommend think about that reading for another 15 minutes, 3 times, whatever you read. Those things initially, at least when mathematics is concerned, mathematics and physics concerned, you read, think through, discuss through your network. That time you will get some understanding, and this should go organically for 3 to 6 months. Then only you will get a proper meaning. When someone is asked, you will be able to go to their language and explain. If they are from physics, if they are from electronics, they are computer science, they are mathematician, you should talk to their jargon, right? For that, we should understand at the fundamental level. Why complex number? Why ket notation? The answer for why, that will create, or that will kindle your interest on quantum computing. Then you will become a confident person who is talking about quantum computing to any people, because that gives you the, how to say, that kick. Then you'll become more interested into quantum computing. So just since I'm talking about the most mathematics, I just came to the way or kind of distraction. Then I want to go back to mathematics. Any question here? Okay, no question.
Maybe why complex number? That is the question.
Oh, right. That is very interesting question, right? See, imagine that I want to measure the number of chocolates in a bag. Number of chocolates in a bag is an integer, right? It is a whole number, or it is a natural number because it starts from 1. That is a natural number. If sometimes if the chocolates goes, it will be 0, right? Now imagine that I want to measure the height of the water bed in a well, assuming that 0 as the ground level the water level can go up above the ground level if you have a container, or it can go below the ground level. Then you have minus to minus x to 0, then positive x, which is whole numbers. And sometimes if you want to refer the water level in between, you need a real number, right? Something like that, the numbers goes natural numbers, integers, whole number, real number. In real number we have rational number, irrational number. Okay, so there are some mathematical expressions to represent these numbers, x equal to 0, x equal to 1, something like that. If I put x square equal to 1 or x square equal to minus 1, you cannot represent this number with any of the known integer or whole real number, nothing you can't represent. That is the reason why a special number is introduced called complex numbers. A plus IB or Z equal to x plus IY. Here the I is the square root of minus 1. So how this is coming into picture into the subatomic scale? In subatomic scale, we cannot measure the particle properties like IIM, the angular moment, or rotation, or strength of the magnetic field, or there are 3 properties known to the as of now we are measuring. And similarly, if you go to photon, if you want to measure the polarization or phase, all those things, those numbers cannot be conveniently represented with a real number, because it represents, or they behave like wave and particle. Whenever there is a duality, we can't use one real number. We need one more number, which is factor of I square. That is why when we talk about anything in the subatomic scale, those states are represented using complex number. Does it answer your question?
Yes, yes. Thank you.
Great. That always think about when we are talking about the quantum computing, go into an electron or try to visualize a photon, single photon, not photons, single photon. Then you will realize we are talking something very, very complicated natural phenomena. That is where you can see superposition, entanglement, inference, these kind of behaviors. Those behaviors cannot be conveniently represented using real numbers because they have the duality nature. So the duality nature must be represented using root of minus 1, square root of minus 1, factor of certain number. That is how we get x plus IY. Right? With this understanding, if you start reading quantum computing related literature, lot of things will come to a clear understanding. And here, for performing certain operations, they are frequently called an operation called Hamiltonian operator and then Hermitian matrix. So this is first time when I start reading about quantum computing, I'm not able to understand what is Hermitian matrix. They mentioned the conjugate transpose. At the time, I don't know. The same question, why complex number? So when the conjugate is applicable only for complex number. Transpose is for real numbers also. If you have a real number vector, we can transpose it. But conjugate transpose is applicable only for a matrix or a vector of complex numbers. So if you only think through a complex number based vector or complex number based matrix, then only you can understand conjugate transpose. That conjugate transpose is a Hermitian matrix. So for any operations, there should be the dagger symbol used to mention the Hermitian matrix. Why Hermitian matrix? Then next concept is inverse matrix, a unitary matrix. Why unitary matrix? Remember this operation, it is this energy is rotating only on the shell of that one. To make sure that the IIM or the energy is rotating at the shell of the electron, it should be a unitary matrix. Then only the magnitude will be 1. I'm not delving into more deeper into mathematics. Actually, in MyQT, we have a special course with a deep dive for mathematics for quantum computing and then physics for quantum computing. Only for selected people who are coming from mathematics background or physics background, not for computers. But sometimes computer program also want to understand these things, because when they are trying to understand algorithm, they can't understand why this operation, why this operation. That is where we kept these two as a courses. So you might now you will realize this is really have a lot of meaning when you go deeper into quantum or mathematics for quantum computing. Here I would like to take pause and then answer your questions. I believe that there will be a lot of questions. Questions? Okay, that's great.
Actually, I have a question about what Subodh had mentioned earlier. That is transportation, and does it contradict cloning theorem in any way?
That is entanglement, right?
No. The transposition, quantum transposition, that is movement of state from one place to the other. Does it have any contradiction with cloning theorem? He did explain, but I didn't get it actually.
Actually, that is no. Yeah, it is cloning theorem. No, it is as the cloning theorem. No cloning theorem clearly states that you cannot create two particles, or you cannot create a particle from another particle. If you try to create this particle will be how to say, it will be destroyed. Otherwise we can't clone it. That is one of the basic theorem. Because of the no cloning theorem, the entanglement was initially considered as not possible. It is not possible to do those things, but actually it is not cloning. It is establishing or creating a mathematical model on their properties, particle properties. So if you have two elements, for example, if you are creating two photons from one single source, you have a choice. Either you can create them as individual photons separately. This photon phase is something different. This photon phase is something different. They are not connected. You can create like that, or else you can create them as an entangled by doing the CCX gate or CX gate, those kind of operations. You can create an entangled photons. Entangled photons, they are not cloning. They are actually two photons. They are not cloning each other, but their polarization or phase or any other particle properties are depending on other. The reason is that they are created such that their the unit or magnitude of that expression is always depending on these two values. We cannot measure separately. So it is simple mathematical model. Assume that you have A and B. There are two numbers. You cannot, to find C equal to, you cannot use A alone. You need A and B. Then only you can find out C. There are a lot of mathematical operations like this, right? If these kind of operations are depending on the particle properties, those two particles, two photons or two electrons, or any quantum system like nitrogen vacancy or lattice, any optical, any quantum systems, if they have created such that their particle properties are connected to each other, that is an entanglement. Here we are not cloning. That is what the no cloning theorem and entanglement.
I think
Does
it
it
was
answer your question, Vivek?
no, it was teleportation. Sorry, I used the wrong word. Teleportation and cloning theorem, whether they contradict each other.
Yeah, actually teleportation also, people are thinking that, see, this no cloning theorem clearly tells that teleportation is not feasible because of the no cloning theorem. So whenever you are teleporting, so actually I'm not very clear about the teleportation or mathematical operations. I have a very vague idea, but I can connect no cloning theorem and teleportation, that I know. Because of the no cloning theorem, teleportation tells that you need entangled two particles. You cannot clone one particle to transport, then this will go. That is not possible. That is what the teleportation in the quantum context. Does it answer your question?
So you're saying that if it teleports, then the original qubit loses its state. I mean, they will not be entangled. That's what you're saying?
No. Only entangled qubits can be used for teleportation.
Okay. Okay.
Yeah. Obviously, it is no cloning, right? Because it is entirely two particles.
Okay.
So the science fiction of teleportation, I don't know whether it is possible or not in future, but this mathematical or quantum teleportation is a mathematical operation. We have a mathematical model for that teleportation as well. Like entanglement, there is a model for teleportation also. Cool, that's a good question. Any other questions from anyone? If no more questions, I would like to go back to some say there is few more slides. I will explain that. Then so the basis state vector. This is very interesting concept. Basis state vector as 0, 0 ket and 1 ket. So when basis state vector, when we talk about basis state vector, imagine this way. Just now I told, right, a bus or moving vehicle can have certain states. Halt, moving, and halt is both, but before starting, after stopping. Halt, moving, crash. These are the three states for any moving vehicle. So we can imagine that a basis state for a moving vehicle is halt, moving, crash. So like that, a qubit can have two basis state only. 0 in the north pole, 0 ket when it is in the north pole, when the spin energy is concentrated on the north pole, or 1 ket if it is in the south pole. Why basis state? If the system is not excited, or if the system is not in the superposition, it will be in either one of these state, or when we measure, it will be either 0 ket or 1 ket. But if it is in the superposition, it will be a linear combination of this basis state. By the word linear combination, it tells that another state vector like this operation, the square root of 2. The square root of 2 mathematically, that is the Hadamard gate operation, but 0 1 1 1 0 1 1 minus 1 root of square root of 1 1 minus 1, that is the Hadamard gate, or else square root 2 square root 2 square root 2 minus square root 2. This is the Hadamard gate. So if we apply this math, if we multiply the state with this Hadamard gate, then that particular qubit will go to the superposition. So in the superposition, it can be in the multiple states simultaneously, but when we measure, it will come down to basis state. Actually, it is also called ONB, orthonormal basis state. So orthonormal, which indicates that it is a perpendicular, then it will come to 0 position. So that is the ONB. So this basis state, you have to understand certain quantum systems will have different basis states based on the particle property what we are considering for processing. For example, the optical quantum systems, they will use different basis state based on the either polarization or phase, but still it is 0 degree or 90 degree. If you talk about polarization, there will be always two basis states only. But if the polarization is changed by a laser activation, it can go to 45 degree, 35 degree, which indicates a superposition. Am I making sense? So if you are able to see any quantum system from the basis state, you will understand any measurement of the system will resulting into the one of these state only. If we repeatedly do the measurement, we will get a answer, probabilistic nature. That is why in quantum computing we are running shots 1024, 2048. That much number of times we have to repeat it. Then comes Hilbert space. Remember, I was telling about the Hilbert space. So the Hilbert space is the subset of vector space. It is called inner product between two state vector written a scalar quantity. Hilbert space is a special space where the inner product is possible, which is an operation that can be performed between two vectors written in a scalar. So inner products give the probabilistic measurement, then the normed vector space. So this is the mathematical representation of the Hilbert space. I don't want to go deeper, but Hilbert space is one of the important mathematical concepts to understand quantum mechanics, quantum computing, and other algorithms. As a final slide with the Bloch-Spear, how Bloch-Spear is used to represent a quantum state. It is psi ket equal to alpha 0 ket plus beta 1 ket, where alpha is the probability of being in the north pole, b is the probability of being in the south pole. So these two probabilities, remember I told you the magnitude equal to 1. That is why it is always, where is that? That is why this is always in the outer sphere. This is the particular mathematical representation. Psi square mod of what is called norm equal to a square plus b square equal to 1, which can be written as inner product of this is very interesting. This is called bra psi, this is called ket psi. So bra psi and ket psi is the inner product equal to 1. We can, if you are put into the polar Cartesian from Euler's formula, it is e power dou I equal to cos theta. Sorry, it is, I don't know what is this one. This, assume that theta, e power theta I, e power I theta equal to cos theta plus I sin theta. So here that e power I theta in psi ket, this is what indicates it's always out in the outer side. So that is how we are getting this psi ket equal to cos theta over 2 0 ket plus sin theta over 2 e power theta I and 0 ket. And this is the angle theta and psi. It is phi equal to psi ket. Quantum state to polar form. This is how it is a polar form. So now you will understand something, because these are all complex number. That is why we have the letter I, and these are all represented inside a geometry. That is why we are able to apply Euler formula and even the standard equation, Euler form, then polar notation, then Cartesian notation. All those things come into picture for complex numbers, not real number. Why complex number? It is happening subatomic scale on either on electron or photon or any other quantum systems. Okay. With this, whatever we have planned, it was done. Now I'm open for questions, question and answer. Any question?
I think couple of slides before you mentioned it's a linear combination. Can you just elaborate why linear is used there?
So usually this operation, it is kind of, if you see, it is the Bloch-Spear, right? The wheel, it is rotating. Oops, my bad. It is rotating here only, right? If it is exponential, sometimes it will go out of that sphere. But if you see, it is always staying in the sphere. How that staying within that, or this formula? Oh, sorry. A square plus b square equal to 1. indicates that this is linear operation. It cannot go exponential or how to say polynomial. That is linear. That's why that linear combination. So any value will be the combination of 0 ket and 1 ket only. There won't be any other new value come into picture. That's why it is the linear combination.
But linear combination with the coefficient being a complex number, that is slightly complex to understand.
Yeah, that is, see, linear combination with a real number we can easily understand, or we can easily imagine. Because for example, if the moving vehicle is moving, the linear indicates that it will be always within the speed. For example, Vande Bharat train is moving at the 120 kilometer speed. It will linearly increase, right? It will start from 0, 10, 20, 30, 40, 60, then it will go 80, then 120, it will stay there. That is the linear, because if it is trying to go beyond linear, we don't know, right? The vehicle and the track cannot handle the speed. So the same thing, if you try to apply at the subatomic scale, if the IAM, intrinsic angular moment of an electron, is trying to move within that a square root of a square plus b square equal to 1, within that constraints, it will be linear only. It cannot go, see, for example, 0 ket, 1 ket, suddenly it cannot introduce b ket or a ket. It cannot introduce. It should be within these two things only. That's why that linear combination come into picture. And that makes sure that we are able to measure the quantum states. Any other questions? It may be for some of you, it may be overwhelming, but believe me, if you keep thinking about this one at maybe 1 month or 2 months, some things will understand. If you keep talking about this one, you will get some idea from somebody, then you connect the dots, you will understand something, then keep on doing that. So this is a kind of consistent efforts. You have to keep on putting consistent effort for the next 3 months to 6 months. Then only you will be able to understand how these mathematics are applicable to subatomic scale, how that subatomic scale behaviors resulting in a computing device. And always remember how this full adder is built into accumulator, how this accumulator is built into arithmetic logic unit, how this arithmetic logic unit is to build microprocessor, how that microprocessor is to build a laptop. Something like that we have to understand. So always remember this particular mathematical model for classical and quantum. That will be handy. Okay, I think if no more questions, I will hand over the session to Christy. Is Christy there?
Hello, KG.
Yeah, yes, Deepa, is Christy there?
Yeah,
Not
yes, sir,
Deepa,
I'm
you.
here. So it
Yeah,
was
yes,
if there's any doubts, then I think we can wind up the session. So the talk were especially awesome. You know, thanks for the speakers, and I think it's time to wind up right now.
I think we can call Pradeep for vote of thanks, and then Pradeep is there?
Okay.
No, KG, I'm handling KG.
Okay, right. Okay. Okay, Deepa, you can handle vote of thanks. Great.
Okay. Okay, once again, good evening. And we have come to the end of the section. So on behalf of MyQuantumTechnology, I express deepest gratitude and extend a warm thanks for this insightful and enriching section on mathematics for quantum computing. First and foremost, a heartfelt appreciation goes to our esteemed speaker, Subodh. Thanks for your sharing your profound knowledge and expertise with us today. And KG, thanks a lot for adding more to the topic. Thank you for sharing your profound knowledge and expertise today. And your presentations was truly captivating and enlightening. We are grateful to all the distinguished participants your active engagement, enthusiasm, and thought-provoking questions have made this section truly interactive and valuable. Your contributions has enabled us to provide this platform for knowledge sharing, learning, and we deeply appreciate your support for our efforts. Last but not least, I would like to thank each and every participant present today. Your active participation and enthusiastic involvement have made this section a resounding success. In conclusion, I extend my heartfelt gratitude to everyone who has played a role in making this section valuable. Thanks, Christy, for your wonderful anchoring. Thank you once again, and looking forward for your continued support in future events. Have a wonderful evening. Thank you.
Thank you. Bye-bye.
Thank you, ma'am. So
Thanks,
now it's
Christy.
time to discuss our session. Thank you, participants. Thank you, speakers. And the meeting is dispersed now.
Thank you. Thanks, Christy. Bye-bye.
Bye.